Well, hello and welcome from my living room here in Fredericton, New Brunswick, Canada. Thank you very much for joining us in the first of what is probably going to be many webinars that Teledyne Caris will be hosting as part of a virtual roadshow that we're putting on to stay connected and in contact with our hydro community as we all do the very important job of sheltering in place over the next weeks. So I'm so pleased to see that we have a great turnout for this session. We held one earlier in the day for the other half of the world, so it's great to see the response. My name is Karen Cove, and I'm the Senior Product Manager at Teledyne Caris. The focus of today's webinar is to introduce you to our new AI platform and the first commercial tool that we're offering on this platform, which is the Sonar Noise Classifier. So we've got two goals today. We want to show you the value of leveraging this tool, and we really want to unpack how it works and open the floor to questions so that you feel confident about making a decision to include a deep learning tool like this as part of your processing pipeline. So I'm pleased to introduce you to our two presenters today. We've got Burns Foster. He is the R&D Projects Manager at Teledyne Caris, focusing on developing new products and services outside of Caris's core competencies. So he previously spent 5 years as the product manager for HIPS and SIPS, which is Caris's flagship processing software suite. And I'm sure lots of you have met and interacted with Burns before. And we also have Tammy Frankson, who is our hydrographic survey product manager at Teledyne Caris. And she's focusing on development ideas and maintenance for products used in her area like HIPS and SIPS and Bathy database. She's been with the company for 5 years after making her start as a field hydrographer, worked primarily in Alaska's Arctic region. I hope that you find today's material interesting and informative, helpful. We're going to start with a deep dive into the what and the how from Burns, and then we're going to move on to a demonstration with Tammy. There's going to be a poll partway through to give a little bit of feedback about what you thought about the webinar, and there's going to be time for some Q&A both after Burns's presentation and at the end. So it'd be really great, as you're thinking of questions, get them in there, and we'll have those two times to cover as many as we can. So that's all I have to say, and over to Burns.
Thank you, Karen. So as she mentioned, I'm going to start with the what and the why, and then we'll turn it over to Tammy for a demo partway through. And I thought it would be useful to start out with an overview, sort of what I've been up to for the last couple of years with the team here at Caris in terms of AI. So it started back in January 2018. We started looking at some of this technology. As a bit of background, for a number of years, Caris has put a lot of investment into expanding our automation tools. So in the software, being able to take the workflows, take the business that our clients are doing day to day and capture those into a process model or a batch process to try and sort of increase the throughput, increase how much data you all can process as part of your work, because of course the sensors are getting higher density results. Everyone needs to do more with less. So that was a big push for a number of years. And we got those tools out on the platform in HIPS and BASE and HPD. We had great feedback, great response, great uptake with those tools. So continuing the conversation after that, we of course, we're always trying to make your life easier. So the next big topic that kept coming up over and over again was, once we've automated the workflow, no matter how well that pipeline works, at some point, everybody had to stop and actually open Subset Editor and just review the data and kill dots. And they still spend a lot of time doing that, particularly if conditions are bad, or your sensor's getting old, or whatever happens, data noise happens basically. So we really wanted to focus next on trying to alleviate the manual processing pain, because that was the next big pain point we got consistently from everyone as feedback. So of course, AI seemed like a really good answer to that problem. So we started in January 2018 with a type of machine learning called support vector machines. And for anyone, particularly surveyors, you'd probably be familiar with a least squares adjustment adjustment, support vector machines in the same mathematical class, I guess you could say, as least squares adjustments, and the math looks really similar, actually. So we started compiling data sets for this algorithm, for training this algorithm. We used a bunch of public data sets. Some clients gave to us for this purpose, things like that. And we started looking at identifying sonar noise. And in parallel with that, with our sister company, Teledyne Optech, who provide terrestrial and bathymetric LiDAR sensors, we started looking at terrestrial LiDAR as well, because they've got really similar noise patterns and really similar problems on the terrestrial LiDAR side as we do in the sonar realm. So we spent close to a year putting all that together. It was a kind of a big effort, pulling these data sets together, getting a team in place, getting the algorithms sorted out, trained up, and then we released just before Christmas, at the end of that year, we released our first beta to a couple key clients. So we went through a beta cycle, gathered some great feedback from them, and the response was fairly consistent. It actually worked really well, which was nice across different data sets we'd never seen before, situations we hadn't encountered. It did work pretty well. But along with that good feedback, we also heard that the support vector machine itself, the way the mathematics works, it doesn't work well on a GPU. So it was still running on the CPU, and it was pretty slow. So despite the performance in terms of how well it classified the data, it took a long time to chew through it. So we kind of regrouped, gathered that feedback, and we started investigating neural networks, because of course everyone's heard of deep learning and neural networks. In recent years, it's on your phones, it's in the cloud, it's everywhere these days. So fortunately, the turnaround from that point was a lot quicker, because we had already gathered the data sets, we had already gathered the knowledge, what was important, what wasn't important in terms of how to train a machine learning algorithm in general on this type of data. Because it turns out there's actually not much research around 3D point clouds with AI. There's some niche interest from things like self-driving cars right now, but outside of that sort of niche realm, there's not a lot of activity around point clouds. So we really had to build a lot of this from the ground up ourselves. So we started that effort in January, and that took us into June. So this time only half a year, kind of get a turnaround on that. And we got a second beta out to again the same group of users. And again, great consistent feedback from everybody on that. And fortunately, we had tackled the performance side as well. So with the neural networks running on the GPU, we really saw a gain in efficiency in terms of processing time and how quickly we get the results processed. So around that same time, we also started branching out. So the terrestrial LiDAR had been going on in parallel this whole time, and we actually had a terrestrial LiDAR beta out at the same time as the sonar one. But we also started looking at bathymetric LiDAR, because Optech also offers a bathymetric LiDAR solution. And that was an interesting problem, because instead of classifying noise, which we actually got to later, we were actually looking at classifying whether or not the laser pulse was hitting land or going through the water column, because as you might expect, the refraction in air is different from air to water back to air. So you have to know where that laser pulse is landing in order to apply the right fraction correction. So we started doing some investigation on that, got some really great results along that track as well. So that one's still kind of in a beta phase, getting close to release. And then in September, we branched out to side scan data. We've been playing around with that. November, we got into classifying bathymetric LiDAR noise as well on the full 3D point cloud. And then, of course, we come to January, where we've released our first commercial product, which is the sonar noise classifier. So that's kind of an overview just of what we've been up to here at Keras. And as you might expect, there's a lot more going on here in the last few months that I haven't put on this slide yet, but you'll have to stay tuned for that. So as part of this AI effort and AI release, we wanted, not just to announce another filter for hips, which in some ways it is, but really it's much bigger than that. So to go along with the sonar noise classifier release, we're also bringing out this new platform. So it's a Keras Mira AI platform. So this is something that's going to serve us into the future for all our AI offerings. So there's a couple reasons we're doing this. Primarily, it's because it's our first cloud service off, at least a commercial one. So there was a big challenge in terms of hardware requirements and everything else that really meant we needed to move to a cloud environment to leverage the scalability of the cloud and the full-time reliability and availability of AWS in our case is the platform we're using. That being said, we were aware that certain clients would not have internet access for a variety of reasons, whether it's practical problem or security concerns or whatever. So we do have an on-premise version of it, but the primary focus for this product is as a cloud-based offering. So currently the product release we have is the sonar noise classifier. We also have a galaxy noise, so that is Optech's terrestrial LiDAR system. That's still in a beta phase. We're still working with some of their clients in a closed beta program that's pretty much close to complete now. And then of course we've got their bathymeter, the seasmil system, their land water classifier, that's also currently in beta, getting close to the end. And then a little less further along is the seasmil noise classifier. So that one's still kind of in a develop phase. So there were some pros and cons to this model, and the hardest part up front for a lot of users is this does require an internet connection. But fortunately, even in the last 2 years since we started this effort, high bandwidth, constant connections, whether it's SATCOM based or it's over the horizon Wi-Fi from certain vendors, and of course lots of our users actually do work relatively close to shore and can maintain a 4G connection even offshore. So it turns out, gathering some feedback about this, it wasn't as much of a barrier as we expect. So by using the cloud service, what that means for you is you don't need to purchase, this specialized GPU hardware, and it's not just the graphics card itself. You also need to buy and spend the money on the equipment to support it. So these things are a big power drawer. So you need a robust power supply in these systems. You need, the CPU and RAM to keep up with it. It's a big effort to put these systems together from an IT perspective. And then once you've got it installed, you've got to maintain it, and you've got that IT overhead that you've got to deal with. By using the cloud model, you don't have to deal with any of that. We take care of it with Amazon. Amazon obviously does the grunt work for us, and we just pick the instance types we need to use from them. So it's great because as new technology rolls out on the market for GPU and deep learning, for us it's fairly trivial to switch to that new technology on the back end. So it's a really attractive model that gets rid of a lot of the IT headaches that everybody deals with day to day. It's also worth mentioning data security. This was something we were concerned about right from day one for obvious reasons, going for a cloud platform. So all of our connections to this platform, whether it's signing up on the website or going to the store or connecting from HIPS, everything's encrypted. So we're using encrypted HTTP connections for that. For better or worse, we also require a strong password when you sign up. So it actually will check that you've got, a special character and a number and a capital letter. And we do that for your own protection. So that's for your data security to make sure, bad actors can't get at your data. But having said that, the other thing we are fortunately able to do is all the data we sent over the wire from the desktop is not only encrypted, but it's actually anonymized as well. So even if someone managed to crack in and get access to that data stream, there's nothing useful in the data stream itself. There's no geographic information contained in that data, but I'll talk about that more in a minute. And one other good point on that is the data you do transmit, it comes into our cloud service, into memory basically. It gets sent to the GPU. The GPU works its magic, comes back, sent back over the wire. We don't actually store any of the results on the cloud service. We don't keep a copy of anything that gets transmitted up. It's just stored long enough to do the classification, and then we throw it away. And in addition to that, because we're running on Amazon, they've got best-in-class security already. They run a significant portion of the web as it is, and they're pretty aggressive in terms of their security monitoring. I've got some fun stories about that if anybody's interested. So that brings us to the sonar noise classifier. So in terms of how it works, there were some key goals with this when we started the initiative. A big part of this was we wanted to integrate seamlessly with the current HIPS workflow. So for any existing HIPS user, we really wanted this to feel familiar. So in a lot of ways, it's almost anticlimactic in terms of it works just like any other HIPS filter does. So you apply the filter, verify the results, and move on. So we tried to make that as seamless and easy as possible. Of course, we're also targeting a significant reduction in the manual cleaning. The interesting thing about this, it's hard to peg a number on this because it really depends on your data. If you've got a brand new system wired up and calibrated perfectly, it's an ideal calm day, and there's no problems, no freshwater inlets or anything else to mess up your day. This noise classifier probably isn't going to bring you a lot of benefit. But of course, I think everybody on the line would know that's probably the exception rather than the rule. So anytime noise creeps into your data, that's when you're really going to start seeing the benefits from applying this technology. So on a moderately bad day, let's call it, you might see a 2 times improvement in terms of time you're not spending killing dots. Or if it's really bad, and trust me, I've seen some data. There's certainly in riverine environments, I've noticed. I've seen some data sets from the Mississippi River in the States. I was just looking at some data from the Port of Hamburg this morning, where it's a turbine environment. the water is really murky. There's a lot of ship noise. There's a lot of stuff going on, and there's no way you can avoid actually a fair amount of noise creeping into the data. And that's where this technology really starts to shine and really gains you that benefit in terms of reducing the manual cleaning time. Another point about this, in the back end, we're actually leveraging our variable resolution technology. So that was kind of the last big thing we did a few years ago in HIPS and SIPS and BDB, was releasing our variable resolution technology that lets us scale a DTM out to any depth and any data density. So we're leveraging that same technology for the analysis of your data. So regardless whether it's high density shallow water, low density full ocean depth, or whatever, the algorithm will adapt to your system so that its single AI model can serve all of those needs. And that also gives us the ability to scale it up to large data sets quite quickly and efficiently. So a little bit about how it works. I mentioned the VR technology already. If you've worked with that before, it basically creates a quad tree tile map of the incoming source data. And basically what that means is in shallow dense areas, you'll get a lot of really small tiles to represent the data set. And then as you go deeper and coarser, the tiles get bigger and they spread out. So we take your incoming data set, we divide that data set up into tiles, and then for each tile, we create a voxel grid. And you can think of a voxel grid, it's a lot like it's a 2D grid, but we're also gridding on the Z-axis. So it's not just the X and Y, but the Z-axis as well. For any parents on the line, if you've got kids that play Minecraft, you'd recognize a voxel grid, which is what a Minecraft map looks like. So we take that voxel grid, and what we're doing is we're effectively binning the data into a 3D binned data set, and we're not storing the scale that goes with it, so we don't know what the resolution is in the cloud when we get it, and we're also stripping out the coordinates. So each voxel tile gets assigned a false 0, 0 origin. So the data that gets transmitted to the cloud and comes back, there's no spatial information stored with it other than the small local reference grid. So that gives us that data and anonymity I talked about earlier. So the data comes back from the AI with the classification assigned, and then we take that voxel grid and we map the result back to the original source points in the desktop. So that's kind of a general overview of how the algorithm works. I mentioned already, it runs as a standard HIPS workflow. So you import and georeference your data, and at that point, instead of creating a grid, you can run the noise classifier, or in parallel, of course. And one thing I want to mention is the AI itself actually doesn't reject or accept data. What the AI does is it assigns a noise confidence to every point between 0 and 100%. So 0 would mean, it's definitely good data. 100% noise confidence means it's definitely noise. And you can kind of see that here in this slice from Subset Editor. The white band here in the middle would be 0% confidence, and then the red would be 100% noise confidence. So back in HIPS, you can set the threshold above which you want to reject points. So that's a separate filter process you can run, or you can run it with the classifier. So you've got the option to do all of it at once, or get the confidence, review it, and pick the threshold yourself after. So it's totally up to you in terms of how you want to apply this filter. So with that threshold, you can get kind of more or less aggressive in terms of the results. If you set a really high threshold, like 80%, you'd keep more data. And conversely, if you set a lower threshold, you're going to start throwing out more and more points. So it's up to you how aggressive you want to get. And a lot of it's really dependent in terms of conditions in your survey, the sensor you're using, all that kind of stuff. So we built in that flexibility across systems to give you that option. In terms of performance, again, it's kind of hard to quantify because it really depends on the system in use, the conditions on the data survey, all that other stuff. But generally speaking, from all the data sets we've trialed, we're hitting better than 97% accuracy on keeping the real data, and about 95% accuracy on removing the noise points. So it's pretty good overall. We do better than that in a lot of cases, but again, it really depends on the system and the environment and everything else going on within your particular data set. I also did some time trials. In this case, I only managed to get a single data set. This was from Shallow Survey 2015 in Plymouth, UK. It was about 9 hours of survey and 20-odd million points, something like that. So I went through that data set. I cleaned it completely by hand, and that took about 6 hours to get, systematically going over every part of the data set and removing any noise points. So that was about 6 hours. I went through a standard cube workflow, and that cut it down a little under half. So by using directed editing, which is kind of the standard Keras HIPS training workflow, by taking about 30 minutes making grids, and then about 2.5 hours of cleaning for that use case. For the SVM, so that was the first version AI we did, you can see see here where the processing was quite significant. So just over 3.5 hours for the processing. But the important part there was we reduced the manual cleaning time down to about just over 30 minutes. So we went from 6 hours down to 2.5, down to 30 minutes with AI. And once we got the deep learning in here, processing time came down by quite a significant margin, obviously down to 20 minutes from almost 4 hours. We brought that right down. Accuracy was still the same. So again, we're looking at about 30 minutes of touch up. So that brings us down to about 6 minutes of cleaning for every hour as a survey. So that's the kind of effect we can get from applying this new technology. And I'd say that data set was moderately noisy. I wouldn't say it was extremely noisy. So if your data gets worse, this ratio is going to get even better. All right. So I think that's everything I had to say.
All right. So we'll move over to Tammy in a moment. I see nobody put up any questions yet. Oh, we do have a question. What multi-beam was the example from?
Oh, and that's sorry. Yeah, that was Rezon's T20. That was the T20 Area 1 data set from the Shell survey.
That's a coincidence, because the question from this morning I was going to bring up for the group was the noise classifier tool, can it be applied to any type of multi-beam data or any specific sonar or prerequisite required?
Right. So we used a fair variety of sonar models and operating environments, let's call it, for the training data set. So we had some shallow water, we had some deep water data, we had Kongsberg, we had Rezon, some Edge Tech, some Norbit. We kind of tried to cover as many bases as we could. And the result with all those different data sets is since the release and trying this, with new users and new data sets is it's very consistent regardless of the multi-beam. So the short answer is it so far from what we've seen, at least, it works with any multi-beam data.
And there was a follow-up question from that too. Was that the multi-beam that you showed as an example with heavy filters in acquisition?
I can't quite speak to. I think it was Pim would have been running that survey for Rezon, and he would have, Pim would be a reasonably competent operator, so he would have had, kind of the standard configuration for a T20 setup.
Yeah. All right. Well, in the interest of keeping on time, let's move over to Tammy for the demonstration part. We've got some questions filtering in now, so that's great. We'll answer these at the end, and please keep them coming. It's great to have lots of questions. All right, Tammy, are you ready?
Excellent. Yeah, I'm standing by.
Great. Go ahead.
Perfect. Well, I'm going to take over with all of you today and move on to the demonstration portion. And for anyone that's not an active current HIPS user, I just want to start out by saying, hey, let's go ahead and get some data brought into the application. So I wasn't going to just drop into the sonar noise classifier. I'm going to show you bringing data in just for a moment so that everyone's kind of on the same page, whether they're current or new users to HIPS and SIPs. So first step, I'm going to be doing drag and drop, where I'm just dropping my data into the application. So I'm going to Tools Options to configure my drag and drop operations. HSX files, these are HiPack HSX files I'm using today. So I'm going to use that configuration. And the only custom settings I'm going to do is I'm setting up where I would like the process data to go. I'm also setting up a vessel file. These are not required. However, this data set does not have offsets or patch test values integrated into the HSX files. So in order to be able to have those offsets brought in, I have to pre-populate the vessel file that goes with this data set. Otherwise, everything else I'm leaving to defaults. Keras is able to self-detect the type of data that's coming in and figure out how to digest the messages and bring it in for processing. As Burns mentioned, georeference bathymetry is one of those essential next steps. This is where we go ahead and basically turn all that multi-beam data into latitude, longitude, and depth. And that information is what we're able to turn into a grid. I'm leaving all the defaults for georeference bathymetry here. We're not going to have a tide. We're not going to load any additional correctors to this data set today, just to kind of slide into and get into what we're all here to see, which is the sonar noise classifier and how we can best integrate that into your current processing workflow. To get started, I'm going to go ahead and just get one line dragged over here and get it to start processing. Oh, I grabbed the wrong one. Sorry. There we go. I'll grab one of these HSX files. Helps if I grab the file I say I'm processing. Alrighty. So while this is going to run, you'll be able to check out my output window here, and it'll show you what's processing. Overview of what steps we're going to run through with the sonar noise classifier. We're going to log into the Keras Mira AI platform and manually run it on a data set that I've got open that I'll show you here in a minute. We're then going to run the sonar noise classifier, and I'm going to run it with the default settings and have it do the rejection of the classified data over 50% so that we can then compare compare surfaces and see how much data was removed and how well it did with the default settings. And then I'm going to go into 3D to do some spot checking around the area and show you what it looks like in 3D. We'll turn on and off our rejected data, query some points, see what values were assigned by the classifier, and then we'll hop out and I want to show you guys that you have the ability to adjust the threshold. So that 50%, rejected or not rejected threshold, we can adjust that in an area by area basis in Subset Editor, or we can do the adjusting of that threshold on the whole data set. And then we also have the ability to remove. So for example, if we'd rejected a bunch of data and we changed our mind, we now have the ability also to remove any of those soundings we previously had rejected. So I'll show you where to go and re-accept that data if you decide you don't want to use the sonar noise classifier on that data set. And then the final thing we're going to do today is we'll show you Process Designer, how easy it is to slip the sonar noise classifier into an automated workflow. If you're currently optimizing your processing already with Keras using our Process Designer and doing some automated workflows, the sonar noise classifier fits perfectly into that automated workflow. So you can see here, I've got one line of data that I dragged in, automatically processed through, and it's already georeferenced, and it created a surface on the fly for us. So this is a surface I could work with or continue to add more data to. However, as I mentioned, we're going to go ahead and use a little bit larger data set. Instead of having you wait for it to process, I'm going to kind of pull it out of the oven in a cooking show manner here, and we'll just move on from here. So we're going to jump into the manual processing. We're going to show you how to do the sonar noise classifier. You have the option of choosing to send the whole data set to the sonar noise classifier at once, or if you're working in a day-by-day processing regime, you could actually use a selection of your data, for example, by selecting maybe just one day of data and sending one day at a time through the sonar noise classifier. So it's totally up to you whether you want to use a selection of noise or a selection of lines or use the whole data set. And it's available once I've got the data that I'd like to use to go up here to Tools, Hips and Sips, Sonar Noise Classifier. And now the first time you run this for the day, you're going to go ahead and type in your username and your password. And if you don't already have an account, we do have a sign up button right here in the application. And once you're logged in, I can continue to send more data up to the Keras Mira AI platform. Once I've logged in, it'll retain my login settings until I close and reopen the application. I also can choose to save my login credentials in Tools Options if I don't want to have to type them in manually every time. You can see here that my selected track lines is the default because I had selected all my lines. Or if you want to change to using all track lines, that's an option to choose the input here at the top. Level of detail and finest vertical resolution. We're going to go ahead and leave these as the default today, as I've mentioned a couple of times. These are going to work for probably 90-95% of the data you're going to put through the sonar noise classifier. These specifically might be helpful in an area where you have mixed sonars. Maybe you have one survey where you have different types of sonars working, or maybe you're in really, really deep water, or maybe really, really shallow water. Those areas where you might have some variation in the density of your data. That might cause you to have to come in here and maybe start to dig into some of these settings to find something that works for you a little better. But again, we've got these optimized so that the majority of users out there are going to be good to go with defaults. This noise confidence filter, again, this checkbox here, if I did not want to reject any data upon running this tool, I would uncheck that box and it would just classify my soundings. I could go into Subset Editor, query them, see what the AI thinks is noise versus not noise, and then choose to filter. But today I'm going to go ahead, check the box, and I am going to have it run the filter and have it reject all noise that is classified as 50 or higher. So again, we're going to notice that the data that gets rejected is going to have a 99 to almost 100% confidence. I'm going to just draw your attention here to the data artifacts that I'm hoping the AI is going to target. You can see that I have these horizontal lines across an entire swath where we either have some sonar interference or maybe another boat driving in the area. So we have a lot of different acoustic interference with this data set, but it would be a little bit of extra manual time if I were to go in and clean that manually. So this is where utilizing that AI would be really helpful. You'll see that also my processing at the bottom left-hand corner of my screen is almost done. Once you see that line green all the way across, that's how you know that basically everything's already been sent to the cloud, and we're basically just writing back those classification values to our individual local point cloud at that point. And again, I mentioned we're running on the cloud platform today. So that's one of the reasons why I wanted to have a couple of additional lines here so you could see how quickly it's able to send the data in its anonymized form up into the cloud cloud, have the classification occur, and then come back and write back to your local on-site data. Again, this was the cloud platform. You do have that possibility for the on-premise, as Burns mentioned, and it is seamless. Whether you're using an on-premise setup or using the cloud, everything is configured in that Tools Options dialog. So when you're running the tool in Keras, the user experience is seamless no matter where your source is. And the other thing, well, I'm going to go ahead, I'm going to get another surface. I'm not going to update the surface I currently have. I'm going to go ahead and just create a new surface so we can do a comparison between the two. And I'm just going to stick this in the same location. And I'm going to go ahead and call this one just _clean. Save and go ahead and get that started. And I just want to remind you while this is going one more minute that this sonar noise classifier is a tool intended to help you with your sonar data cleaning. And Burns talked to you about how it can really help to advance your cleaning timeline and get you to the review process faster. So we're not intending to replace a hydrographer's eyes on the project. We're merely hoping to help you get to the end where you're doing review and doing that complex analysis faster. All right, so I'm going to go ahead and use our our swipe tool, and I'm going to go ahead and turn on and off that dirty, unclean surface so that we can then get a peek at the clean surface below. So as I swipe this to the right, you'll see that the noise in this upper left-hand corner that was kind of off the edge of the survey has all been removed and taken care of. And then you'll also see those horizontal stripes that are across the entire swath. All of those have been taken care of, both in the deeper area and this shallow area. Same thing over here as well, that all of these artifacts that are occurring across the entire swath are able to be removed. All right, so next step, we're going to go ahead and just hop into 3D mode and subset really quick. All right, I'm just going to hop in and look at some of these horizontal bars that were on that unclean surface. And we'll be able to turn on rejected and show you what they look like. All right, I'm just going to go ahead and turn off my compass and my lighting for you for a minute. And I'm choosing to color my data by line here. So if you're wondering what my current color scheme is, we're coloring by line. So every individual line of data is showing up as a different color. Now I'm going to go ahead and turn on my rejected data. And once I've turned on my rejected data, this is where you're going to see what results in those horizontal bars, those artifacts across the survey area. So you can see these arcs underneath the survey where we've got some interference with our acoustics that's causing that punch through of the seafloor. All of this was rejected. And you can see if I go ahead and select some of these points and query them, I can go in and see exactly how they were rejected. Under status, they were rejected by our noise confidence filter here. And if I go over here to the right, I can actually see what that noise confidence classification value was. And again, just as a reminder, the classification value, this is what is coming out of our sonar noise classifier. It's not what's rejecting the data, it's just assigning this classification. And then we're using the filter additionally to say, filter those items, for example, that had a classification value of 50% or higher. So again, I'll just query a couple of these other points over here. Those other ones were 90, these were 100%. So again, the algorithm was 100% certain that this was noise. If you wanted to adjust that filter, you can go over here to the surface filter. These are where our filters exist in Subset Editor that allow you to adjust that threshold in an area by area basis. For all the data that's opened in Subset Editor, I can adjust that threshold. If I go to filter type noise confidence, if I check the include rejected button, this is actually going to go ahead and filter the data that has previously been rejected. So for example, if I said, you know what, threshold 100%, I don't want to actually reject anything and go ahead and apply it with the include rejected included, you'll see that all my data is actually brought back right away here. So again, just another way that you can say, you know what, I want to remove that filtering I did when I sent the data to the noise classifier. I could also choose to maybe be a little less aggressive. Maybe I wanted it to be 85% instead of 50%. I can go ahead and hit apply. And again, as we saw, these were all 99, 100% certain. So all of that same data was taken away. But you have the ability to adjust that threshold here manually in Subset Editor, but also in tools when we're outside of the Subset Editor. If we decided we wanted to change the entire data set to maybe be 85% instead of rejecting all the way down to 50, I can do that across the entire data set as well. One last thing I want to show you in Subset Editor before we leave is that I was colored by line originally, but I can also color by confidence. Confidence being that classification value. And you can see here that the areas where there is a higher confidence and a lower confidence. We've got a lot higher confidence in this red area here, and you can see this blue, which is kind of the top of this rocky area. Maybe adjust my point size so you can see a little bit better. That these are the areas where the algorithm was a little less sure And again, if I wanted to query some of those points just to see what those values were, confidence, so it was still a little bit less. So it was 5. What was the red? Had my colors backwards. 0. Okay. So everything in red was 0. It was very confident that was the seafloor. And then the blue is starting to highlight anything that was not the zeros. So again, it helps you to bring your idea or bring your eye and draw your eye to those areas where the algorithm was less sure or more sure. So again, using that color by confidence is a really tool. I'm running out of time. I'm not going to save changes here. I just want to show you one other thing really quick before we go into subset editor, before we go into the process designer. We have the ability, as I mentioned, if you wanted to undo all of this rejection that we've been doing, maybe you wanted to try the algorithm out, but you decided, you know what, in the end, it wasn't the right fit for this data set. We want you to have the confidence to know that you can go ahead and try these filters, but you're not stuck with the results. What I did is I went to the edit. I'll do this again really quickly. I went to the edit dropdown, status flag, and I can reset the HIP status flags. So here I could specifically go ahead and say, hey, any data that was rejected by the noise confidence filter, go ahead and re-accept it. And this will accept any lines, whether you want to do it on just a couple lines or the entire data set. So this is how you can turn all of those rejected flags back to accepted to not leave any effects of this filter. Additionally, I mentioned that you have the ability to adjust that threshold on the entire data set. So again, I still have all my lines selected. I can come up here to HIPS and SIPS data filters, and I can get that same process depth dialog where I can go ahead and say, you know what, instead of 50%, maybe I wanted to adjust that filter to be, 77, 80%. And I could go ahead and run this on the selected track lines or again on the whole data set. So again, be confident knowing that you have that full control to adjust what you want that rejection threshold to be. Alrighty, so we've talked through kind of manually working with the sonar noise classifier, how you can interact with it, clean data, verify, and work with the data. The last step I want to talk about today is the automated workflows. So being able to bring your data through your traditional workflow and just add the sonar noise classifier as a process. I've got the typical workflow set up here where I'm bringing in my raw data. I'm using a conversion, putting it into a specific project. I've got my georeference bathymetry stage, which is just, again, leaving all my defaults. I didn't set any tides or corrections. And then I have my add to HIPS grid where I've got that swath angle _ 4 meter clean. That's our new surface that we just created. I'm going to just interrupt this pipeline here, delete one of these connections, and I'm going to add the classify HIPS noise step. So again, this is that new additional filter step where we're going to go ahead and put that item in. I can go ahead and set up whatever settings I want here. I'm just going to go ahead and use those defaults with the 50% threshold and the same level of detail and finest vertical resolution. And then I just made the connections, passing my track lines from georeference bathymetry into the sonar noise classifier step, and then back out to add that data to the grid. So that's all I had to do to a traditional processing workflow to be able to bring this new tool into my processing pipeline. So I can go ahead and I can save this process and go ahead and use it in our application. And then to run that automated process here, I just go up here to Tools, Run Process Model. You can see that my process model was saved out here in the main directory _ sonar noise classifier. And then the only step that I have to fill out here, because I pre-populated all the information, is the data I want to process. So if I wanted to select one more line of data just to put in here, I can go ahead and do so. And that's it. So it'll run through all of those processing steps that took place when I dragged and dropped the data in. It's going to run the sonar noise classifier for us, and it's going to add that line of data to the gridded surface, that swath angle 4 meter clean surface that I had up and ready to go. So there you have it, folks. A quick 20-minute overview of both manual use and the automated workflow for being able to incorporate the sonar noise classifier into your everyday workflow. Well, this is processing. I just wanted to draw your attention really quickly to this idea of what's next. Burns, gave a really great overview of what we've been doing and just reminding you that the Keras Mira AI is the platform for future AI offerings for Keras. And so the sonar noise classifier is our first option, and we have many more that we're looking to add to the platform here in short order. So everything relating to potentially object detection, classification of soundings for objects, being able to identify objects in imagery. We have a whole bunch of different ideas that we're working with, and I'm really looking forward to seeing what Burns' team is going to put out as our next offering. But stay tuned. This is just kind of the beginning of our AI experience here at Keras. And again, you can see here it only actually took a minute to process that one line through the entire workflow. But if I close this out, I'm going to turn off that unclean surface, and my new line of data has automatically been added right here, and everything is good to go. So it's that easy. And you you can see, I don't have the before, of course. This line I added is actually one of the worst with the vertical lines and horizontal lines across here. All right, well, I think that's the end of what I had to share, Karen. So I think we're going to go ahead and start the poll.
Yeah,
We've got 6 questions.
Yeah, and while folks are filling out the poll, we can have a peek at those questions, and you and Burns can pick a few to answer live here.
Yeah, sounds great. I'll let Burns go first.
All right. There is a question about, let's see. You mentioned the AI classifier performs well in noisy, shallow, dense data sets. How well does it perform in deeper, sparser data sets? We actually had a number of deep water data sets in our training pipeline as well. I've been pulling down various data sets from NCEI, which is NOAA's bathymetric sort of cloud web service for all their data holdings. I actually got a data set from 2011, I believe, where they sailed from Guam down to the Mariana Trench and back, which was kind of fun because it went from about 100 meters down to obviously 11 kilometers, which is about as full ocean depth as it gets. And I processed that entire data set between those two depth ranges in one pass with the noise classifier, and it worked great the whole way. So it performs well in both the deep as well as shallow. So a lot of that comes down to the scaling in terms of variable resolution. So we're rescaling that voxel grid so that the deep water data ends up looking a lot like shallow when it goes to the AI. And so the AI just sees a consistent image.
Very cool. I can answer another question here. I see that we've got one that says it's a bit off topic, but there was another question that asks if there was a way for the process workflow to monitor a directory and bring in new files as they're saved. There actually is. We have a Keras software called Keras On Board. So Keras On Board is an additional offering that has a lot of the tools able to run a process design, just like in HIPS and ZIPS. But Keras On Board wraps up a map interface in addition to the directory monitoring, and it's able to go ahead and pick up and process that data as soon as it recognizes that those files are no longer being written. So again, we'll monitor that directory, pick up any new data as soon as it's acquired, so that you then have the data ready to go and review as soon as you drive your boat, back to the office. That's the intention, where you can already have Keras process through everything before you get back to the dock, and no more waiting around processing before you can go in and plan your survey for the next day. So again, that's our Keras On Board product.
There's also a few questions that have come in through the chat panel. I'm not sure if either one of you are having a peek in there.
Yes, right, I was. There was a question about interferometers, which is a great question. I had mentioned early on that the worse your data is, the better it performs. And not to criticize interferometers, but they can be a challenge. They can be quite noisy, and we've seen really good results. We actually had Kongsberg reach out to us with some geoswath AUV data they were struggling with, and we were able to clean it up quite quickly for them, which was kind of fun to see. And we have a good relationship with Kongsberg, so that's always nice. Another good question. 2 lines that are valid, but they have a tide bus perhaps. The AI's pretty good about it. It's really good at looking for planes, so it kind of depends on a few factors. If they're really close, the AI does tend to pick one surface over another, and it will go for the shallower one, as you might expect. So if you can avoid your tide busts or correct them somehow, obviously that's ideal, but if not, it still does its job.
I can take that next question that's in the chat window. Can you talk about throwing a new SBET example from reprocessing with delayed ephemeris data onto an already processed data set? So what I would do is that I would have that, just a second, I would take that SBET and I would go ahead, and that would be an additional process design that I would run. So I would have just a couple of steps loading in the SBET and rerunning the georeference bathymetry step. So again, that is a post-process step. That's not something that you could run currently with Keras On Board. That would be just a secondary process design you would kick off as soon as you could potentially get your data opened in HIPS and ZIPS after you get back to the dock. So again, SBET loading and reprocessing, basically rerunning that georeference bathymetry step is the only additional step you have to do, and then you're able to be up and running.
I think I will close off the poll here, and I think we just wanted to wrap up by making sure that everybody knows that we would love everyone to access these tools and evaluate them for themselves. And we've got a promotion called Bring the Noise. And basically for HIPS users who want to try it out, all they have to do is go check out the Keras website, and we'll direct you to a 30-day trial of the sonar noise classifier. You just have to sign up and that's it. And for those who aren't HIPS users, or if you would like to have an extra copy of HIPS in order to do some in-depth testing, we are trying to facilitate that as well with a free month of HIPS Essential and the sonar noise classifier. So all of that is all described on our website. And if you're interested, you can just go navigate and contact our sales department, and they'll help you get set up. So I wanted to put a big thank you out to Tammy and Burns, and thank everyone for tuning in. If you said yes to receiving communication from us when you registered for the webinar, you'll be getting a link to the recording of the webinar along with a transcript of the Q&A with all the answers written out. And if you did not consent, then you feel free to email me or go through our contact sales portal on our website and we can get you a copy. So I very much appreciate your attention, and please keep an eye out for the other webinars that we'll be delivering over the next couple months. And there's one in particular in April that I think the folks that signed up for this are probably going to be quite interested in. And what we're going to do is explore the use of automation in Keras Onboard with Mira AI and our cloud services in support of remote surveys. You know, we realize that a lot of folks are not working normally right now and not able to go out and do their surveys as usual. So we just want to bring everybody up to speed with what we can do to facilitate getting people back to work. So good morning or good afternoon or good night, depending on where you are, and thank you very much.